you going? They said, we're going to Amsterdam. I said, what a coincidence. I'm also going to Amsterdam. What are you going to do there? They said, well, we're actually going to go to this commemoration thing. And I said, wait a minute, you are actually going to go to this commemoration thing? And I was so happy. I thought these people are going to sit on a train for 2.5 hours to go to this commemoration thing and then travel 2.5 hours back. That also meant that I had to spend 5 hours with a couple of students on the same train in one day, but we had good conversations. But it was a good evening. So it really is exciting times for general relativity, yes? All these things that are being discovered right now, and I heard a couple of things last night during that commemoration about upcoming events. I mean, I just look at the gravitational waves. But if I can share just one of the experiments that they were doing that I was not aware of. Do you know about the NICER experiment? Have you heard about that? That is NICER, yeah. It's, as you know, physicists always come up with a nice abbreviation for their experiments.
Is it a telescope or a satellite?
It's mounted on the International Space Station.
I think I heard the name, but I don't know
Okay,
exactly.
well, it really is cool here. I mean, I sort of only heard I only knew a little bit about this experiment, just from elevator pitches or something like that. Here's the experiment that people are doing. It's the NICER experiment. I have no idea what it stands for, but and I'm sure they picked up a couple of nouns and adjectives such that the beautiful word came out NICER. Okay? So the idea is if you have a pulsar, and as you know, a pulsar is this neutron star that sends out a beam of light. And suppose that the beam of light comes from this particular patch of the neutron star, yes? So the thing orbits around its axis. So that means that every now and then, like a lighthouse, this beam of light passes the Earth, and you can actually measure that and learn something about magnetic fields in neutron stars and gravitational effects and such. And what this NICER experiment does, it's an optical telescope mounted on the International Space Station. It does the following. At the moment that this patch that emits the light, by the way, it's not like it's completely shell is opaque and there's this one little lighthouse glass there that sends out a beam of light, but the magnetic fields operate in such a way that it is as if there is one patch of light being sent out. Here, at the moment that this light is on the other side, if you would assume Newtonian physics, that flash of light, that ray of light would just go, away from the Earth, away from where you could see it. But of course, in general relativity, around the neutron star, you would have a Schwarzschild space-time. Not exactly true, it's a curved space-time. It's the space-time of a rotating black hole. And we've only looked at static black holes, the Schwarzschild ones, 2 weeks ago. But you would still have the same light bending effect. So when the patch that emits light to the other side of the neutron star, Newtonianly speaking, it would be sent out towards infinity, but because of the curvature of space and time, a little bit of that light is being bent around the thing towards Earth. So that means that even if the beam of light starts in the wrong place, namely at a place where Newtonianly speaking you would not have seen it, you would still get some of that light. And that telescope, that NICER experiment, actually measures the full beam, including the part that you would see if the patch is on the other side of the star. And it gives you all kinds of beautiful information about the neutron star that you otherwise would not have obtained. Now that is a pretty cool experiment. So this experiment makes full use of the fact that light itself is being bent by gravity, and there's almost no NICER. There's a nice pun there. There's no night. Come on, it's funny, okay? Well, I tried my best. Okay. There's almost no nicer way of commemorating the light bending experiment of 1919 by doing the same effect on neutron stars, the light bending thing. It was really cool. It was a really cool evening. So it really is an exciting time to do general relativity, not just because of the black holes and the gravitational waves and the optical pictures of black holes, but even these sorts of things. It really is exciting. Speaking of gravitational waves, that is the topic for today. We are going to talk about gravitational waves. You might say we're going to save the best for last because today is our last main lecture of the course in general relativity. If people cannot really want to hear more about this, as you know, we might have a master's program that has a full course in general relativity and an additional course in gravitational wave physics. We will see in 2020-2021. Okay? Do not take this to any competing universities because at the moment it's still tentative. We're working on it, what I'm saying. But Given the scope of our course, we do have one lecture devoted to gravitational waves. Can I just ask, out of pure interest, what is your current understanding of gravitational waves? And yes, I know some people have done a project on the thing, more than one in this group actually. It's also more than 2 and also more than 3. Just anything. Gravitational waves.
Distortion of space-time?
Yes.
Due to moving objects?
Now, the distortion of space-time, I agree with that. So is a black hole, by the way. Right? Distorts space-time.
But if it's
in fact, you distort space-time right now.
Yeah.
Okay.
All right. But if I move,
Yes.
I'm creating like a distortion of space-time,
It's a moving
and that will
distortion.
propagate.
Okay. So the distortion of space-time is certainly part of the story, but that by itself does not define the gravitational wave. The gravitational wave, of course, I mean, I'm leading, I'm teasing a little bit. Of course, everything that has mass and energy will distort space-time. What particular type of distortion makes a gravitational wave? I saw some hand gestures here. So
Orbiting.
Orbiting of black holes
Okay.
or neutron stars.
I hear orbiting and another one.
Collision?
Sorry, collision of two things. That works.
Do you necessarily
Okay.
need an orbit?
Acceleration.
I hear acceleration. All acceleration, by the way, or do you need a particular kind of acceleration?
Maybe
So
just-
what we heard were examples. Yes, there was the collisions. There was the orbiting. Sure. But the underlying mechanism here, yes, is acceleration. But that's not enough. You need a particular kind of acceleration. Not any acceleration will make gravitational waves. I'm just curious if you have an idea on this. Not a test, it's just interesting.
Circular acceleration?
Circular acceleration, what does that mean?
Accelerating like in a spiral.
Oh, that it spirals in.
Yeah.
I think.
And that does work. Collision, by the way, also makes a gravitational wave. That's not circular acceleration, though.
I think you can't have linear acceleration. It has to be like your acceleration can't be parallel to your velocity. Like if you have a velocity vector and you accelerate in the same direction, or you will decelerate in the same direction, I don't think that changes anything. You have to like go somehow on the curve.
And well, any acceleration will be along its own path. Yes. In that sense, it's sort of like a tautology.
What?
You're saying that if something is moving this direction,
Yeah.
its acceleration must be in any other direction.
Yeah.
Otherwise, it
Yeah.
must have an acceleration, but it cannot be along the same line that it
Yes.
is already traveling. Okay. Any other ideas? By the way, doesn't need have to be the source of gravitational waves. Just what are gravitational waves? Whatever comes up. Any idea how fast gravitational waves go, for instance?
Speed of light.
It seems like obvious, right? Speed of light.
I mean, it's massless. So.
Okay, but wait a minute. It's massless, so it must go with the speed of light. That is special.
I mean, I'm not sure. I just assumed it would always be the case.
That is not the first time that your intuition proves correct. Everybody here, one exception, has done special relativity, and what you have seen there is that in order to have something go with the speed of light, that thing must be massless. And the arrow also points the other way. If something goes with the speed of light, it is massless. If something is massless, it must go with the speed of light. No exceptions to that rule, and that still holds in general relativity. Now, that means that a gravitational wave, whatever it is, if you want it to go with the speed of light, it has to be a massless thingy. Okay, is it?
Space-time itself doesn't have mass. So.
That is true. It's a distortion of space-time, right? So it's not like an object, it's actual space-time itself that is just doing some traveling. And yeah, and by this argument, you can immediately conclude, well, it must go with the speed of light. Now, back to the source of gravitational waves. Yes, you need an acceleration, but you need something, a particular type of acceleration, namely one that is called a quadrupole acceleration, but we will get there in due course today. Okay? So, what is a gravitational wave? Yes, it's some distortion of space-time, but one that actually wants to travel. So you cannot have a distortion of space-time that stays local. You're allowed to have a distortion of space-time that may be changed in time, but it should not be local. So it has to travel, and by this argument, if it does travel, then it must travel with the speed of light, if only for the mass is zero argument. Now we will actually find that conclusion as we just go through the maths today. So I think we have a clear objective, yes? We're going to see gravitational waves and we're going to end up finally with an expression that will allow you to calculate what a gravitational wave will look like in principle for every source. And when a physicist says in principle, you have to hold your wallet, because it just means that the mathematical expression exists. Whether it's helpful in practice is a second question. But we will find a full solution under a number of conditions. So that is the plan. In order to do so, what I would like to do is start by talking a little bit about the Einstein field equation. We've touched upon it a couple of times. We have sort of a hand-waving idea where the thing comes from. What we've been mostly doing in this course is, given a metric tensor, calculate what the physical effects would be of things, right? Christophel's and geodesics and everything. And we've also discussed certainly that the metric tensor itself comes from an equation like this, Einstein field equation. In order to do our gravitational wave physics, we have to understand this thing a little better. So I would like to spend a little bit of time on this. Now, we touched upon this equation twice in previous weeks of this course. Do you remember where this thing comes from? If you would have to give an hand-waving argument, forget about the mathematics, just hand-waving arguments. Why does the thing look the way that it does? If you don't know, that's fine, of course, because we haven't had a full course on this, but maybe you'll remember.
Then you just look at Newtonian mechanics and try to figure out what gravity would be in a non-bent space-time.
That's pretty good.
And then just, well, plugged in the constants in front of the
Yes.
tensors.
Well, you make a valid point. There's two constants in here. All of this stuff, this side, is just rewritings of the metric tensor, yes? If you have your metric tensor, this thing, you can construct this thing, you can construct that thing in a way that I will specify a little bit more today. But all these R, business, and the G mu nu is all just metric tensor stuff. And this, as we've also touched upon before, is just the amount of energy and momentum that you have in the universe. And this is what the equation tells you, yes? You tell me how much matter and energy there is in the universe. In other words, what this tensor is, T mu nu. And then in principle, I can solve for the metric tensor by solving this equation, because all of this is metric tensor. Now, where does the thing come from? Yes, there's two constants in here. And Einstein, as smart as he was, knew that the equation, whatever made a metric tensor, a curvature of space-time, and you know curvature of space-time is a way of describing gravity due to the equivalence principle. If you want to connect matter to a curvature of space-time, he knew from a mathematical theorem, it's called Helmholtz's theorem, that it has to be a combination of this thing, and the only thing you have to look for are these numbers.
Is the T mu nu thing always all the energy in the universe, or does it depend what metric tensor you're looking for?
No, it's always the energy. Well,
But what if it's
universe.
more local?
Well, when I say universe, I just mean that patch of the universe, or that patch of space and time, where that particular metric tensor applies.
So
when I say
T mu nu is not the same in every situation?
No. Oh, sorry. No, when I say universe, I do not mean always take as a metric tensor the whole of the cosmos and the planets and the Magellanic Clouds and everything and put that in. It just means if you want to have the metric tensor of this particular lecture room, I have to calculate your masses and your motions and all this stuff, put it in here, and then I would have, in our little local universe here, that is this classroom, I would have the T mu nu. So yeah, that's heavily situation dependent. So yeah, then you have to find these numbers, right? So this Helmholtz theorem tells you there has to be a number here and has to be some number there. What are those numbers? And this is where Einstein thought, well, two conditions. One of them is, if you go to, this is Felix's suggestion, right? That if you go to a situation where gravity is very weak and things do not move too fast, so not speed of light fast, then whatever metric comes out of this must give you Newtonian gravity. Now, just by that fact alone, he could specify what this number should be. This is why there is this Newton's constant G in there. And for the people who were there last week in the break, Ali, that was your question actually. She asked where the pi came from. That had to do with the Poisson equation of Newtonian gravity, if you would like to rewrite things. If you have no idea what I'm talking about, forget about it. It's not important right now. But this is where that constant comes from. Now, there's another constant, that's the 1/2 here. We also touch upon that a little bit. And that is simply the conservation of energy. That if you want the universe, you assume that the universe has this conserved amount of energy and momentum. If you want, that means that the derivative of this thing with respect to both space and time should be 0. Then the derivative of this left side with respect to space and time should also be 0. Right? What holds for the right hand side should also hold for the left hand side. And if you apply that condition to the left hand side, then you see that the only way that the total derivative of this thing is 0 is when this number is 1/2. So if you think about it, there's very little physics actually that goes into finding this equation. Yet the equivalence principle, that tells you that you can write gravity as a curved space-time in the first place. You had the condition that whatever you do, it has to be some connection to matter. That says, well, then this Helmholtz theorem must hold. You have the conservation of energy, that gives you the 1/2. And it should give you Newtonian gravity, that gives you this crappy constant that you have over there. I say crappy because it is so small, right? You need an enormous amount of matter, an enormous amount of T mu nu to make space-time curved. So this is all there is to it. I mean, in retrospect, everything sounds so easy. Now, I want to introduce you just to one additional way that you could have found this. This is not how Einstein did it, but for the people who are interested, I'm going to show you another way, and I'm going to do it very hand-wavingly, because this will take you, well, not one rainy Sunday afternoon, but several of them. Do you remember Lagrange mechanics? Do you also remember how that worked? You have an action. The action is defined as
Minimized.
yes, but before we minimize, we have to put something here. It's an integral, and that has to be minimized.
Of the Lagrange.
Yeah, it's the Lagrangian integrated over time. In this case, it will be proper time. Right? It will be the natural choice. Yes.
Was that just the same thing that we did before with looking for the path of the shortest time and then
Yes.
integrating that one in order
Yes,
to get
it's the
to-
same mathematics. It's applied in a different way, but it's the same mathematics. When we derived the expression for the Christoffel symbols, we also did it in the same way. We said that the path that massive particles take through space-time should be such that the proper time is minimized. We wrote down an expression like this, and then we looked for the expression that minimized it, and that was the Geodesky equation. That's how we got there. The same mathematics applies here. You have to see here the Lagrangian. Now this particular Lagrangian, the one that gives you your curved space-time, should obey an extremely important condition. Namely, it should obey the principle of relativity. Now you might have to think a little back what the principle of relativity means. We discussed it in special relativity, certainly. Is anyone who remembers that? It's been a while.
The invariance of the speed of light and the invariance of the laws of physics.
It was the invariance of the speed of light, and it was the invariance of the laws of physics. I was looking for the second one. And if you recall from special relativity, I do not particularly like the starting point that the speed of light should be invariant. The Minkowski light element should be invariant, but sure, you get to the same conclusion. Do you all remember that the principle of relativity in relativity says if you go to some other coordinate frame, you should end up with the same laws of physics? That physics does not care whether you try to solve it from this coordinate system or the other coordinate system. You should always get the same physics. Denying the principle of relativity is saying that apparently nature has a preference for this coordinate system from which you do your physics, and all the other ones are wrong. Okay? Maybe that's how nature could have been. In fact, in antiquity, this is how people thought that nature was. Nature should only apply on Earth, and all other coordinate systems are just simply wrong. But people found, you know what, maybe all coordinate systems are just as valid. That's the principle of relativity. So that means if you're going to write down some theory of physics, it should be such that it holds in all coordinate systems. Agreed? That also means that if you're going to get your laws of physics from Lagrangian mechanics, from some integral of the Lagrangian, then the Lagrangian itself is not allowed to be different from one coordinate system to the next. Do you agree with that step? if you want whatever comes out to be the same in all coordinate systems, then whatever the Lagrangian was to begin with should have been the same in all coordinate systems. So one way to do this is to find yourself some Lagrangian that is completely made up out of metric tensors, right? You're looking for something that tells you how the metric tensor looks. So this thing should be made out of metric tensors, but in such a way that whatever comes out for this L, this combination that you're looking for metric tensors, itself is going to be the same for all coordinate systems. Is that a logical step to make? If you're going to look for the laws of metric tensors, then you have to look for a Lagrangian that's going to be the same for all not for all metric tensors, but for all coordinate systems. So whatever you're going to pick for L, it has the condition that it has to be made of metric tensors and must be invariant. If you go to some other coordinate system, your Lagrangian is not allowed to change.
Why must it be made of metric tensors?
Because we're looking for a law that gives us how metric tensors look. So the metric tensor should be in there, right?
Okay.
There's one ingredient missing. What is the difference between special and general relativity? When do you apply general relativity? When do you apply special relativity? It's all the way back to week 1. When do you apply special relativity? When do you apply general relativity?
Special if you're in an inertial frame.
Exactly. If you are in an inertial frame, then you apply special relativity. If you go to some other frame, a non-inertial frame, you have to apply general relativity. How do you get to a non-inertial frame? From an inertial, suppose you start an inertial frame, you want to go to a non-inertial frame. How do you get there? What kind of coordinate transformation do you have to do? Can you just Lorentz transform you to another frame? Would that be an inertial frame?
If you're in a non-inertial frame, how do you get into an inertial frame?
You put it the other way around. If you are in an inertial frame, you want to go to a non-inertial frame. You have to accelerate. That means you have to take 2 derivatives. Okay? So that means if you're going to make this thing and you want to have to apply to non-inertial frames, you're not really looking for the metric tensor, you're looking for second derivatives of metric tensors. That's what you're looking for. It's a second derivative, accelerations, that brings you to non-inertial frames. So, 3 ingredients now. Whatever the Lagrangian is, it must be made out of metric tensors, because otherwise you will not end up with the metric tensor theory. Secondly, it has to be invariant. Thirdly, it can only consist of second derivatives of the metric tensor. So, this should be, a second derivative. So what we are really looking for is a Lagrangian that is some particular combination of second derivatives of the metric tensor. And it must be invariant. Again, back to week 1. How do you make an invariant? If I give you a tensor and I wanted to make an invariant, we did this with 4 vectors. See if you can recall. You contract it with another 4 vector, yes? If you want to make an invariant out of a 4 vector, contract it with any other 4 vector. Doesn't matter which one, any other one will do. Agreed? We did this in week 1. So, that sort of gives us an idea of what this Lagrangian that we're looking for should look like. In order for it to be invariant, it has to be a contraction of the second derivative of the metric tensor, well, with some other tensor, because otherwise you will not end up with an invariant. But this other tensor that you're going to contract with is itself only allowed to be a metric tensor or a second derivative of a metric tensor. Right? We have to make this thing only out of metric tensors.
Why can't it contain other terms that are not metric tensors?
You can, but then you have to explain what this other thing means physically. What does it bring to the table?
Okay.
I mean, what you're suggesting now is if we're going to take this thing and contract it with something else, then we're really saying physically that the curvature of space-time, the metric tensor that you're looking for, is connected to some other piece of physics that corresponds to your external tensor that you put in.
Or maybe it's just mathematically sound.
Yeah, but every mathematical object in physics has some physical meaning, right? You are very right. Of course, again, mathematically speaking, as long as you contract this thing with any other tensor, you will end up with an invariant. So that's all fine. Now, I propose to contract it with things that themselves only consist of metric tensors, because right now I'm just looking for how metric tensors operate in physics. You are right. You could also contract it with some other tensor. That's fine. But then you're introducing that the curvature of space-time is coupled to something else, physically. Which is true, by the way. It is coupled to matter. Agreed?
Yeah.
So you can also contract it with something else, and that will probably give you something about the amount of matter and energy in the universe. Now, the question that you can then ask is, okay, what is this combination of contractions of second derivatives of metric tensors to itself that brings you an invariant? That thing will give you something that's called the Riemann scalar, and I'll introduce it more properly as we go along in this lecture. Although you probably know this thing, you've seen it.
Is this just a standard R, or is that different symbol?
It's an R.
Okay.
Unfortunately, in general relativity, two symbols that are constantly used are G's and R's.
I mean, I don't mind, I just wanted to be sure, because
No, it's-
the R there looked a bit weird.
No, I'm sorry, this is the standard notation. It is R. So, here's an R that has two indices. It's called the Ricci tensor. Here's R, by the way, that is that R. It's the Riemann scalar.
Is that the Lagrangian? Is that L?
Yes,
L
this is
equals
your
R.
Lagrangian.
Okay.
R.
So it obeys the Euler-Lagrange equation.
Yes. So what you can now do is that you stick this in, use your Euler-Lagrange equation, right? Because one rule of all the whole throughout the theoretical physics is whatever nature does, it will try to minimize this number. So you can use your Euler-Lagrange equation to look for whatever the metric tensor has to be in order to make this Lagrangian, this R, minimized. And then if you take 2 or 3 lazy Sunday rainy afternoons, you end up with this equation. That's another way of doing it. It takes a lot of mathematics, but I think it is a very clean way of doing it. You take this rule that you know holds in physics, namely actions to be as small as possible, minimized. You just have to look for the right Lagrangian. What Lagrangian do you take? Well, the one that consists of second derivatives of the metric tensor. The metric tensor because you're looking for a metric tensor theory, curvature, space-time. Why second derivatives? Because you're looking for non-inertial frames. And why an invariant? Because the principle of relativity tells you that whatever comes out should be the same in all coordinate systems. And then you find that this is a logical candidate. Put that in, solve the Euler-Lagrange equations, get this equation. It's a lot of algebraic work. Wouldn't recommend it if you have nothing else to do. But this is another way of getting that equation. Okay? Now, still haven't talked about gravitational waves. In order to talk about gravitational waves, I have to give you what the Ricci tensor is. My plan is the following. I want to look at if I disturb space-time by a small amount. I have a space-time, a metric tensor, and I give it a little push, or a little tick. Then I will have my space-time plus a little something on top of that. I just introduce myself. And my question is, how will that little thingy that I put on top of that, how will that evolve through space-time? That is just solving this equation. What I'm going to do is the following. I'm going to say, you know what? The solution to this equation is always a metric tensor. Let's for simplicity say, you know what? Space-time is just Minkowski. It isn't, but you know, as a first approximation, let's say it is a Minkowski space-time. And on top of that, this is the little tick that I give. There's Minkowski space-time, and I slightly hit it just for a second. This could be your collision of two black holes, right? Slightly hitting space-time.
Is that an H?
Sorry?
Is that an H?
That is an H, yes, that is the standard notation. Now, giving space-time a little tick, you might think, you know what, that is, collisions of two black holes is not a little tickly-ish, okay? That's a huge collision of things. But here is where this smallness of this number comes into play again. even the collision of two black holes gives you enormous amount of energy, yet it still has to multiply by an enormously small number. So as far as the metric is concerned, it is still only a small perturbation. So you can play this game. You can say, you know what? I'm going to look for the solution of the Einstein equation, where I'm assuming that the background space-time is just Minkowski, and somebody gave a little tick as in collage two black holes together or something like that. That produces this thing. The plan is this: I am going to put this thing into there, work out the mathematics, and what we're going to find is a differential equation for this unknown tick that I gave. How this thing then itself will evolve through space and time. This will be your gravitational wave. And all these things that we talked about, that it goes with the speed of light, for instance, will automatically come out just from the mathematics alone. So do you see the strategy here, what the plan is? In order to do this, us actually putting this thing into that thing, well, I just have to tell you what these symbols mean. Okay? I've been putting that off because all this time we've been able to talk about space-times because I just gave you metric tensors. And now I have to do a little bit more. We're actually now actively going to use the Einstein field equations. So, now if you want to know why this thing, the Ritchie tensor, has the form that it does, feel free to take your 5 lazy Sunday afternoons and go through these calculations. Okay? So, the why I'm going to skip. I'm just going to give you the definition. Now, I don't use this definition on a daily basis, so I always have to look it up. Here we go. There's equations that you know by heart, and this is one that I rarely use, so I actually have to look it up. I've told you before, it has to be a second derivative thingy of the metric tensor, otherwise you would not agree with non-inertial frames. But the first derivatives of the metric tensor are already encapsulated in your Christoffel symbol, right? The Christoffel symbol is a particular combination of first derivatives. So if you want to get second derivatives, you can just take derivatives, single derivatives, of the Christoffel symbol, and that's ultimately the same as taking a second derivative of the metric tensor. So you can write this Ritchie tensor in terms of derivatives of the Christoffel symbol. And again, this I always have to look up because I simply cannot remember it. Note the contractions as I go. There you go. And I'm sorry, I should have made this an alpha beta. There you go. That's the Ritchie tensor. Don't think too long and hard why this is true. It's a definition of the thing, yes? If you go through this exercise and you end up with this equation, then you will find that the Ritchie tensor is given by this expression. There's no physics there. The physics was in solving this set.
What kind of Christoffel symbols are those?
Just your basic Christoffel symbols that you know. That you know and love.
Well, yeah, but you mean you have multiple weird indices. You have the row, and then you have in the end something that looks like a 1, but probably isn't.
This is a lambda.
Oh.
This is it, yes.
Well, okay, but still, I mean, they're more than usual. What instead of the three that we have, 3 indices that we have, usually you have 4, 5.
Well, each Christoffel in here has the usual 3 indices, right? I might have named them differently than what we usually. We usually call them
Yeah.
alpha, beta, or mu and nu, or something like that. But I just don't have enough Greek symbols here to get all the indices named. So I had to borrow some extra Greek indices. I took a rho, for instance. It's the Greek letter R. Botching up your beautiful alphabet here, I'm sure, but that it's meant to be a rho.
Okay, yeah, no, sorry, it was just, no, all good. I was confused for a second.
How many equations have I written down now?
A lot.
Yeah, tell me how many.
64, no? 64?
64.
Wasn't it?
No, more than
For
that.
each index is associated to 4 equations.
This is so each index has 4 equations, yes. So there's 4, but for every alpha there's 4 betas, so that gives you 4 times 4, 16. And somebody came up with an additional factor of 4, 64. No idea where that came from. 16, you would think maybe. It's a little bit less though. It's 10. Can you tell why?
Symmetric.
Symmetric. Ritchie tensor, we have the fortunate luck that it has only 2 indices, so at least you can write it as a matrix. Or one of these indices tells you what's in a row and the other one tells you what's in a column. 4 by 4 gives you 16, right? Now if you look at the definition of the Ritchie tensor and you would swap alpha by beta, you will find you will get exactly the same expression. So if you would swap a row and a column in this matrix way of presenting the thing, you'll get the same thing. Here you can already see it happen, by the way, because this Christoffel symbol, as you know, is symmetric in its lower indices. So this thing by itself is already symmetric. If you go through the rest of the terms, you will find the same conclusion. So that means up to 16, all the ones below the diagonal are the same as the ones above the diagonal. Now I just do some counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are 10 equations. With an enormous amount of terms, right? Because look, there's a contraction here. And wait, there's more. Here's a contraction of the Christoffel symbol with itself. It's like a self-contraction. More terms. Here's a contraction with itself, and here's a contraction of this Christoffel with that one. Now, I don't even want to do the counting. You get an enormous amount of terms. Not even take into account that the Christoffel symbol itself is a contraction of many terms. So if you want to write this out in terms of metric tensors, I have no idea, 128 or something like that terms. So again, I don't think Einstein was joking when he said that the summation convention, the way to write contractions, really was one of his biggest contributions to science, because nobody wants to write down 128 terms. Okay? So, this here is the Ritchie tensor. We have one more number in the Einstein equation that is unspecified at this point, namely this number, this thing that we call the Riemann scalar. The Riemann scalar is simply defined as follows. Do not think too hard what it physically means right now. Let's just say it follows directly from this strategy to get the Einstein field equation. You will get this thing out. It is, by definition, the Ritchie scalar double contracted with the inverse of your metric tensor. How many equations? Equations.
Counting the Ritchie tensor as 1 or as the 16 that it is?
The question, how many terms are there and how many equations are there? The question is how many equations?
It's 1.
Yeah, and usually what we do is we count the indices, right? And then we say each index count corresponds to 4 equations. So if you will, you can just say, you know, the number of indices, 4 to the power 2 of that number is the amount. Right, that's how we got to 16 originally here before we invoked the symmetry argument. Now we have 4 to the power 0 maybe, because it has 0 indices. Do some highbrow math here, 4 to the power 0, that gives you 1. Also indicated by the fact that there is really just one extra symbol here, no indices, okay? So, it's one equation, but how many terms? So here's a contraction, the muse, and the muse is an additional contraction, double contraction. Sorry?
4 terms?
Well, each comes with 4 terms, right? Every mu comes with 4 terms. The mu comes with 4
Yeah, but
terms.
the tensor doesn't.
But you
Yeah.
add them.
Well, in principle, you would say 16,
Yeah.
right?
But you add them, right? You
That is true, but my question is how many terms? How many numbers are you adding? It will be 16. And yes, and then if you would then also put in that the Richie tensor itself, these 5 million terms a piece, it again becomes a huge, very big number. So, but we are going to have to deal with these things if we are going to put this thing into the Einstein field equation and find ourselves a differential equation for the metric tensor disturbance, this h mu nu, what's going to turn out to be our gravitational wave. So, does anyone feel like writing down 128 terms to go through this whole calculation? You should. I mean, that's the only way to do this. I mean, there's really no way to get around this, yes? If we're going to put this thing into that thing, we really have to write down what this is, we have to write down what that is, and then add everything together. Huge amount of terms.
Are there nice programs that automated the entire thing?
Yes. In fact, just for people who have nothing to do, last week or so I uploaded these lecture notes on cosmology. In one of the appendices there's a Mathematica program that you can just copy paste into your Mathematica and it will do the thing for you. Now obviously I would not ask this of you if it didn't so be the case here that life becomes very easy. Because we had said that this thing, this is what is going to be our gravitational wave, the little tick that we gave our Minkowski space-time is going to be small. That is usually well justified again by the fact that this is a small number, so whatever you change to the gravitational field, your Minkowski space-time, is probably going to be a very small contribution indeed. So, we're going to assume that h mu nu is much smaller than the numbers that you have in your Minkowski tensor. Or if you want, that means that it must be very much smaller than unity, yes? Minkowski tensor is -1, 1, 1, 1. And making this one small just means that whatever the contribution is, it is much smaller than unity. So these are 16 numbers. Again, 10 if you take into account the symmetry. These are 10 numbers that you're looking for, and each of these numbers has to be smaller than 1. If you do that, and again it's justified by the fact that it's very, very difficult to make a gravitational wave, so whatever gravitational wave you have is probably going to be very small. So this is probably going to be a very small number indeed. Right? But you know the numbers from popular science or maybe lectures on gravitational waves, right? The metric disturbances that you find for two colliding black holes or two merging black holes is typically of the order of magnitude of 10 to the power minus 21 as they arrive on Earth. So it's ridiculously small. So this is an extremely good approximation. Now, that makes life very simple because that means if we're going to put this into the Ritchie tensor and then later on in the Riemann scalar, many things are simply going to drop out. Some things are going to drop out because Minkowski tensor consists of constants, and that means the constants will just give you 0 Christoffels, right? Christoffel is a derivative or combination of derivatives of your metric tensor. If the metric tensor is constant, the Christoffel is going to be 0-ish. Secondly, this one was Helix. Secondly, if this number is small, that means that every time that you encounter in this huge amount of terms here a product of two of these small numbers, h mu nu is, I don't know, a small number, but you multiply it with itself at some point, so in this combination, that is going to be very small indeed. So we are going to throw away all terms in these 5 million terms here that come with h mu nu squared, where two h mu nu's enter in the same term, because we're going to assume that that is very small indeed, which is true. If this number is small, then this number squared is smaller still. That is always true for numbers smaller than 1. So, we're going to be helped here in writing out this stuff and this stuff by the fact, two facts. One of them is that the Christoffels corresponding to the Minkowski tensor are 0 anyway, identically 0, take derivatives of -1s and 1s. And secondly, that you're going to end up with terms that are squared in the small perturbation in your gravitational wave and therefore can be ignored. This is an approximation, but it's an extremely good approximation. That's going to make our life very simple. In fact, we can immediately write down what the answer is. But before that, Felix, please.
So, I mean, right now we're just ignoring every h mu nu term, right?
Why is that?
If you always say, well, it's much smaller than the metric tensor,
Yes.
and don't take it into account for your Riemann, not Riemann, for your Ricci tensor.
Yes. No, that's not what it says.
Only if it's square. But you wouldn't assume that the square makes much of a difference then.
No. That is true. The square is not going to make much of a difference. I agree with that. Okay,
Yeah.
so all the square parts we're going to throw away.
Yes.
Alright. The non-square ones I'm going to retain. Fine. But of those non-square ones, many of them are going to be 0 simply because we're going to take derivatives of the Minkowski tensor.
And what I was just wondering about is if you are dealing with an order of magnitude of 10 to the power of minus 45 anyways, how does the squaring make much of a difference then? Because I feel like it shouldn't have an effect. Like compared to how small the number is, the squaring shouldn't really matter, right?
Yes,
So
but now you're mixing up two parts of the Einstein equation. There's one part that tells you how space-time is curved,
Yeah.
and additionally there's how much energy in matter there is. I'm just talking
yeah.
about the left-hand side at
okay,
this point.
yeah, I'm sorry.
So, but it's a good question, because in fact I am going to put this to 0 in a moment. Not by approximation, but because I'm going to be interested as a first step in our way towards gravitational waves. I'm first going to be interested in, do these things exist even in vacuum? Now, people who've done electrodynamics would probably not be surprised that the answer is yes. Many of you have done electrodynamics in the last period. And you might have remembered that one of the things that we concluded, I think in week 5 of that series, was that electromagnetic radiation even existed if you put the sources in the Maxwell's equations to 0. So you can have an electromagnetic wave even in vacuum, even if there's nothing for this thing to travel through. That was one of the big conclusions that we had there. And we're going to see the same thing here. So in a moment we're going to set this to 0, this equation, which is another way of saying whatever this gravitational wave is going to be, I'm going to look at it as it travels through vacuum, and just to see whether that thing exists. And already gave away the answer is yes. Then later on at the end of the lecture, I'm going to reinstate this thing, and we're going to find, okay, how does it look like if there is matter around? That's the plan. Now, back to Felix's question, the smallness of this number at this point is just a statement about the left-hand side of the equation. Has nothing to do that there happens to be also a small number at the right-hand side. Separate issues at this point. Okay? So, I promise that under these approximations, we can almost immediately write down what the Ricci tensor is going to be. In fact, it's going to be ridiculously simple. In order to do that, we have to find the Christopher's. Right? We need to take derivatives of Christopher's. So yeah, we first have to calculate the Christopher's. Now, this is one of your favorite pastime exercises. See the last couple of weeks. Let's make a little side note. Let's calculate Christopher's.
How do we know what h mu nu is?
We don't. That's the whole object.
Oh, yeah,
We don't
true,
know what it
yeah.
is. We're going to find what it is.
Yeah.
We're just going to assume that they exist, and then check what the equation tells us what they should be.
Okay.
And then we find the properties of gravitational waves. One of you came by today in my office and asked, what if on the exam are we going to get metric tensors that are not diagonal, and that we then have to calculate the Christoffel symbols? Because if you remember, this is the inverse of the metric tensor, which is very easy if the metric tensor happens to be diagonal. If it's not, then you have to do some work first before you get the inverse tensor that you need for the Christoffels. Do not worry. That exercise in the exam, where you have to calculate Christoffels, is going to be an exercise where the metric tensor is diagonal. Okay, so you would have no trouble. If you're going to have trouble with calculating this from a diagonal metric tensor, then no, what can I say? Let's write down the Christoffel. This is one that I actually do know by heart, because this is one that I do use on a daily basis. Well, close to daily basis. And the first thing that I do is make a mistake. 2, in fact. There you go. It's okay to make mistakes as long as you correct them. So I'm sure somebody told me that. That That's just a definition of the Christoffel symbol. Now,
Do we have to know that by heart?
no, you're going to get this. No, you're going to get this. I think everybody should know this by heart, right? Also people outside of gravitation physics, also people outside of physics, also people outside of science. This is just one of these things that you just have to know by heart. It's like knowing that traffic lights, when they say green, this is when you get to walk, or that Australia, where somewhere on Earth that lies. Same thing, you have to know what a Christoffel symbol looks like. This is a Christoffel. Let's put in our metric tensor. Now, we can talk for a long time, a short time about this, but let's be as brief as possible. You can immediately see that if you're going to replace each of these ones by this, this is Minkowski, yes, that this derivative alpha on this part will always give you 0, right? This, not necessarily, generally not. We have no idea what h mu nu is, so we cannot say that the derivative is 0. But that means that immediately we can find that these derivatives only work on this gravitation wave that we're going to look for. So let's just replace these g's by h's. This is not smuggling, this is literally what happens. It's just taking derivatives otherwise of constants. So you will get this. Right? So, good. Everything between brackets has now been substituted for the gravitation wave that we're looking for. We still have one g in here, that's this one, and that's the inverse of your metric tensor. So this thing is the inverse of that thing, and that's exactly that question. We can easily diagonalize, we can easily find the inverse if this thing is diagonal, right? Now, the question, is this thing diagonal? Well, this is. But is this thing diagonal? We don't know. The only thing that we know about this number is that we assumed it to be small. We have no idea whether it's diagonal, what its properties are. So, that means, unfortunately, if you want to find the inverse, you cannot use the trick that you just take the 1 over the numbers of the diagonal one in the metric tensor. You have to do a little bit more work. That's a sucky exercise. But we have this condition. And that said, we were only going to look for expressions that contain only one h mu nu per term, because an expression that has 2 of them is extremely small indeed. So, if I'm going to replace this by a Minkowski metric tensor plus this h mu nu, and I'm going to multiply this out, I'm sloppy in my phrasing here, it's a contraction, but you know what I mean. Then you're going to end up with expressions that have 2 h mu nu's in there, and those were going to be small, right? So by the fact that this is, each of these terms already has 1 h mu nu in there, means that this one is not allowed to have any of them in there. Otherwise you end up with terms that have 2 of these h mu nu's. That's good news, because that means by approximation, I can just say, you know what? Let's take the Minkowski there. This perturbation, this extra perturbation that comes from the gravitation wave multiplied by the ones we already have are going to be completely negligible. And now we are in the situation where I wanted to end up, namely that we now have our Christoffel symbol, if you will, to first order in this unknown function h mu nu, this gravitation wave that we're looking for. This is the Christoffel to first order in h. This is fancy way of saying that there's only 1 h per term. Good. Any questions so far? All clear? Because now, let's take these Christoffels to calculate the Ricci tensor. Right, we're slowly working our way towards the Einstein field equation. Claim. 0, 0. Please convince yourself that that is the case, and for what reason.
Are both of them 0, or is one minus the other 0?
No? Separately.
Okay.
Individually. They don't cancel out. They are 0 apiece. Approximately 0, I should say. Any takers why this is the case?
Yeah, you have contraction of the Christoffel with itself, in a sense, or two Christoffels. And in each Christoffel there are first order terms in H.
Okay.
When you contract them, you get second order.
Everybody seeing this? This is a contraction of two Christoffels. And we already saw that the Christoffel itself is at the very least first order in H. So you're going to take a Christoffel and put it next to another Christoffel. This whole term will have two H's. And those we're going to throw away because they're going to be very small indeed. So by extremely good approximation, these contractions of Christoffels with themselves are going to be 0. They're of second order in H, as you would say. Well, that makes life easy. Because you just end up with these two. That's what I wrote here. So Ritchie tensor to first order in H. Now what remains to be done at this point is that you take this Christoffel to first order, put it in here, and work out what the result is. It's just some algebra, right? There's no difficult tricks here. The only thing you have to do is just take this expression, put it in there, and see what you end up with. This is just algebra. I'm going to give you the answer. You can already guess what's going to be at least one exercise in the tutorial later this afternoon to do that calculation. I'm leaving that up to you to do simply because there's no physics here, it's just going through the algebra. So you will end up with the following. This thing will give you so again, put this thing into that, work through the algebra, you will get this expression, and I'm going to take a moment to introduce the symbols to you. I introduce some new symbols to make the notation nicely easy to read. I introduce this new tensor here, V. It's just shorthand for the following combination. You know, this is when, if you look at these things, everything looks extremely complicated, but because of all the different EDCs and everything. Now, again, put this into what we know is the first order expression for the Ritchie tensor. You work through the algebra and you will find this. Note that it only contains h mu news, this gravitational wave that we're looking for, the perturbances to the Minkowski spacetime. All the non-Minkowski or the Minkowski parts have dropped out because of the Christoffel symbol. Yeah. The Christoffel symbol killed all the Minkowski parts because their derivatives were 0 everywhere. So this expression for the Ritchie tensor is now solely in terms of h mu nu, this thing that we're looking for.
What is the square again?
Yeah, what is the square again? People who have done electrodynamics, do you
Is it
remember
a
what that is?
nabla but for fourth thing?
Sorry?
Is it a nabla but for fourth thing?
Yes, almost. How about Felix, just for you, I put a square here, so it's like a nabla square for four
Okay.
things.
That's the D'Alembert.
Yes, yes, we call the thing the Lambertian. Electrodynamics people might recognize this. If not, or maybe it's too long ago, that's fine. Again, go through the algebra, you will find the expression. I will just tell you what it is. This thing, box, is, or box squared, depends on the author, so might want to ignore the square depending on whose notation you follow. Is by definition means minus twice the time derivative plus the spatial derivatives. That's his definition of box conversion. Yes, Felix, if you look, this is Nabla squared, agreed?
Yeah.
You said, well, it's like a four-dimensional Nabla squared. That's true, because you now have a time thing, but because of relativity, you get this thing with the minus.
Yeah, no, I mean, it makes sense.
Yeah, it does, right?
It's a nice symbol
Yes.
from the triangle.
There's even more there. Again, you won't be there, unfortunately, next year to do electrodynamics, but there's all kinds of beautiful properties too, just the one version alone. See YouTube videos on electrodynamics period 4.
You can still watch your lectures.
You don't have to, okay? As long as you like and subscribe, by the way. I'm almost at 300 subscribers right now. I saw 297, so it's only took me 5 years, but slowly we're getting there. Probably won't get rich on that, but okay, guys. So, long story short, we know what this thing is now. We're still not done because we still have to calculate the Riemann scalar. And the Riemann scalar is the Ricci tensor contracted with the metric tensor. Now, if only nature had decided to be not so difficult. If only nature had decided that only one coordinate frame was the correct one, it also correct. Okay, so we never had to transform to non-inertial frames and get all this stuff in the Einstein field equation. Unfortunately, nature decides every coordinate frame is the same. Nature's like a communistic coordinate system policy or something like that. Everybody should have the same rules. Now, there's good news here. One of the exercises in tutorial is going to be the following: that if you are going to look at vacuum alone, that means no matter and energy present, an empty classroom, no air, no nothing. That means this is 0. Then the Einstein field equation tells you that this combination must be 0, right? One of the exercises in the tutorial is that it suffices to prove that this one is 0. You can already see, sort of see it happening. Yeah, be careful here. I mean, if this is 0, then this is necessarily 0, right? Because this is just a contraction of the Ricci scalar. So if this is 0, then this must be 0. Fine. If you know that this is 0, then that is 0. Agreed. I'm asking the other way around. If you know that the answer is 0, does that mean that the Ricci scalar is 0? So it's true. If the Ricci scalar is 0, then this combination is 0. Is the opposite also true? That is not trivial. That's an exercise. But let's assume that it is. It is. That means we're not going to bother to calculate this. Okay? Instead of saying all of this must be 0 for the gravitational wave to exist in vacuum, we're just going to say the Ricci scalar itself must be 0. I'm going to erase this. So we're going to put this to 0 because we're interested in how things look in vacuum. Here's the exercise from tutorial. Then you can show that this is also true. Again, the other way around is easy. If the Ricci scalar, if a Ricci tensor is 0, then obviously this combination is 0. I'm asking the opposite, not trivial exercise. But once you have proven this, then, well, we also then know that whatever the gravitational wave is, this combination must be 0. That's the only way that it can fulfill general relativity. Now, we're going to have a break in a moment. Let me just introduce some terminology. Any space-time for which this holds is called Ricci flat. It's an important terminology because, as we just discussed, Ricci flat means that you have a metric tensor of which its Ricci corresponding Ricci tensor is 0. And we saw what that corresponds to the universe, or a piece of space and time where there is no energy or matter. Okay. Here's a famous example of Ricci flat space-time. Minkowski space-time is Ricci flat. You might think, oh, well, that's obvious. Minkowski flat, therefore Ricci flat. That's true. The other way around is not obvious. If something is Ricci flat, it could still be a non-Minkowski space-time. Schwarzschild space-time is Ricci flat, for instance. Again, that's an exercise.
But then if r mu nu is 0, is the whole left-hand side also 0?
Yes.
But then how could Schwarzschild space-time still be Ricci flat?
Again, that's an exercise.
Because T mu nu would not be 0, there's still mass.
Again, exercise.
Okay.
One of the exercises is show that this is true for Minkowski, well, that one is obvious.
Yeah.
Show that it's true for Schwarzschild, and then investigate whether it's true for Robertson-Walker.
I don't see how it's true for Schwarzschild.
Again,
I mean, I'm
exercise.
sure you can prove it mathematically, but by definition, the energy momentum tensor would have to be
Yes,
0.
you ask correct questions. I mean, no, really, they're good questions, and I'm just deliberately not giving the answer.
Fine.
But I will say the ultimate conclusion. Schwarzschild spacetime is Ricci flat. Your question is valid. How can it be Ricci flat if there is mass there? To be continued.
We'll find out.
Okay, you will find out by hopefully by tonight. Okay. Now, so what we have here now, just to wrap up the first half of today's lecture, Einstein field equation. We looked at where the thing comes from. We introduced then what the Ricci tensor is. We didn't do a full derivation, but I gave you the steps how to get there if you were so inclined. You get this thing, then we said, you know what? Let's say that you have a Minkowski spacetime where something has happened that sort of made spacetime a little bit curved by a small amount, and then calculated if this amount is small, how that thing, this unknown tensor, would itself move through this spacetime by plugging it back into the Einstein field equation, and I set it to vacuum. So whatever we're going to find for this h mu nu is going to be whatever this thing does as it travels through the universe, not encountering anything. In fact, all of this brings us now to the equation that after the break we're going to solve. We saw that this is where we need to be, that the Ricci flat universe that we live in right now, right, that we're now talking about, to first order in h mu nu is this expression, and it has to be 0. So, minus one version, if you want you can put a square there, copy it from there. Unknown perturbance h alpha beta plus the alpha v beta plus the beta v alpha has to be 0. This unknown perturbance that we have, photobomb, this unknown perturbance that we have, whatever general relativity wants to do with it is all in this equation. So if we can solve this equation, then we know how this perturbance will travel through the universe and what it will do as it goes along the way. Not surprisingly, this is going to be a gravitational wave, and this equation will tell us that it will go with the speed of light and such, these things. But this we will do after the break. So, any questions so far? No? Going once, going twice? Okay, then let's have a break. Yes. You want to know?
Sorry.
Was it me or was it the board?
Oh my god.
No, it's just I've seen 2 pictures on Facebook where in the last 2 years where I was memed by students because I happened to appear on a picture.
I've seen those.
Oh, both of them you have? Okay. Or don't tell me there's more. I've seen
There's a
2.
few.
Oh, okay. Well.
Nelson has them.
Who was?
Nelson.
Nelson.
He's a
has them.
distributor.
Yeah.
He's the meme distributor.
He's the, okay, okay, so you know who to go to. Anyway, I'm pitching this book here. We see many books, some on just on general relativity. There's our main book on gravity, right? The book by Hartle. If you're interested in just gravitation wave, only the physics of gravitation wave, then this is your book. It's a book by Maggiore. If you talk to gravitation wave physicists, say Maggiore, they all know about this book. It's a book only on gravitation waves. So just to give you an impression, right? Note the thickness here. But what we are doing right now is only a very small snippet of gravitational wave physics. Just to give you some idea of the things that we're not treating right now. And
When was that book written?
this is-
Before we actually discovered that?
Yes, this is about 5 or 6 years old, so it's not that old. And the guy, Maggiore, who is an Italian physicist, I think from Pisa, is, according to all accounts, is writing the second version of the book now, or the second volume of the book, where he deals with the actual measured gravitational waves. So this was very close to the first detection. In fact, let's look it up. When it was written, I think it's 2011 or so. 2008. Michele Maggiore. There he is. Sorry,
Is that
for
good,
all the
Simon?
accents that I sort of can pretend do, it's Italian, okay? And I do it very crappily, I'm sure.
It's too forced. Be more natural.
Yeah, that's, yeah, okay, yeah. Maggiore. Better, yeah?
It's already done.
Really sounds like Manjora.
Okay.
Mission Manjora.
Anyway, guys, so this is a very good book, and one of the things that we are not treating right now is we are just looking at if you have a gravitational wave in Minkowski background. But of course, gravitational waves are typically produced in neutron stars, black holes. So that means you have to replace this one with a Schwarzschild black hole, with a Schwarzschild spacetime. But that means that all these nice trickeries that we did here to make life more simple, right, where all these derivatives of the Christopher's and so dropped out, will certainly not happen there. You see the Christopher's of the Schwarzschild background. Things become much more complicated, that's one. Let alone if the black hole can spin. There's another metric tensor for that, it's the Kerr black hole. Kerr space-time becomes more complicated still. And an additional effect is, these gravitational waves send away energy from the system. But that means if something is orbiting two stars around each other in this very complicated Kerr or Schwarzschild black hole, and on top of that you have a gravitational wave, and it's taking away energy, that means that the way that they orbit around each other will change, right? Because you're stealing energy from their orbital motion. But that means the gravitational wave itself will change still, and will send out an additional amount of energy. And this, so back and forth between geodesic equations tells you how things move, given that you've stolen energy, and how things move then determines how much gravitational wave you have and therefore how much energy you steal. So you go back and forth between the two, and it's an extremely hard problem. Now this book deals, amongst many other things, on how to solve that problem, how this is done. And then there's all stuff about detection of gravitational waves and sorts of things. So if you're interested, this is the book for you. I'll try not to say too forced right now, Maggiore. I know what you mean, by the way. When people, when foreign people do pretend Dutch, okay, they always highly exaggerate the gutturalness. You ever notice that?
The what?
Yeah.
Yeah.
That's not Afrikaans.
Yeah, exactly. Yes. Yes. But nobody in Dutch actually speaks with this gutturally, do they?
Afrikaans people do.
Yeah. Okay, Afrikaans.
Yeah.
Well, I certainly know that Maastricht they don't.
Yeah. Yeah. They sing beautifully.
Yes. Yeah, but I'm from the north. I'm a Hollander, so I'm allowed to, I guess. Now, so let's continue. You know where we are right now. This is where we ended up. We've assumed that there is a perturbation to the Minkowski spacetime, and then if the thing exists, then general relativity tells us that perturbation must obey this equation in vacuum. Now we're going to solve this equation and then conclude how this gravitational wave will move through space. I'm just going to stand here just for a second so I'm sure it has some usage. So we're going to conclude how the thing will move through space and time, okay? You're getting used to this now. It's a mathematically crappy expression.
Yep.
Because you're looking for 10 numbers, right? H alpha beta has 10 numbers, it's 2 indices, but it's symmetric. 10 numbers that you're looking for. So that equation seems safe. That equation will tells you that you are looking for 10 numbers. So this is really a set of 10 equations, and again with many terms apiece. In fact, you can already tell how many terms, by the way. Can you tell? 10 equations, right? Because for There's 10 numbers that we're looking for here, but how many terms per equation? I would guess 60, yes. Yeah, I think that's right. I think that's 60. Or maybe it's 10 by some symmetric reason I'm not seeing. But anyways, it's a complicated system that you have to solve, agreed? And you've seen this before with the geodesic equations, that are coupled. For every combination of alpha and beta, these v's bring in that every alpha beta is connected to some of the other 10 numbers. Right? So you have 10 equations that are very highly coupled to each other. That's extremely difficult to solve. So having to solve this, hard work. Yes. And again, there's a trick that's going to help us. Now, going to lean just for a second on the experience of the people who have done electrodynamics. For the people who haven't, don't worry, we're going to go through this in a moment. Do you remember in electrodynamics, just talking to those people right now, do you remember electrodynamics that sometimes you had an equation that is very difficult to solve?
Yeah.
What? There was a cool trick that you could make the equations much more simple.
Symmetries.
Not symmetries. Close them.
Homogeneous?
Sorry?
Homogeneous?
Homogeneous? What's even?
Like when we said that fields can propagate through a vacuum, you just make one whole side 0. That makes it easier. Yes.
And I'm thinking before that, if you're thinking specifically about electromagnetic waves, way before that, do you remember that at some point we were looking for the solution to differential equations that gave you the scalar and the vector potential? But they were extremely complicated expressions.
Oh, gauge.
Gauges.
What are gauges?
Yes, that is exactly what we're going to talk about now. So for the people who have seen this before, very good, we're going to use the same trick here. Now, what I'm now talking about, this is for the people who have not seen it or for the people who need some remembering. It's always good to hear this another time, second time, third time, fourth time. The idea is this. It so happens that every now and then in physics you find yourself with a mathematical equation that is very difficult. But on occasion, you also find that you can make the mathematics more easy by using some mathematical trick. Usually cleans up the equations that you have to solve without changing the actual physics that comes out. Sometimes mathematics just tells you a little bit too much about your system. And sometimes it just so happens that you can clean up all this superfluous mathematics or use it to your advantage, that you end up with the same physics, just written in more easy mathematics. Now, again, for the people who have done electrodynamics, and again, for the people who have not, don't worry about it. It's just for completeness for the people who want to connect it to their previous course. You might remember that at some point, we saw that you can write a magnetic field as the curl of the vector potential, and that you could write the electric field as minus the gradient of something that we call the scalar potential, minus the time derivative of, again, this vector potential. We discussed this. We also saw that, unfortunately, the equation that tells you A and the equation that tells you phi were very complicated. Were extremely long, complicated expressions. But then we found this mathematical trick. And yes, we're going to use the same trick in general relativity in a moment. We found the following trick. We found that if you have a vector potential and you would replace it by, well, just again the vector potential, but now plus the gradient of any number that we call lambda. It's not a number, by the way, any function that you call lambda. And you would replace phi by the phi and then minus the time derivative of the same function. Do you see that you have now changed your potentials? They used to be this, but now you add and subtract a little bit, you get different potentials. You can mathematically show that despite you having changed your A and your phi, your resulting electromagnetic field has not changed. That was good news, because this is the stuff that you measure in the laboratory, and the A and the phi are just mathematical objects that you use to make predictions. But the fact that mathematically you were allowed to change up your A's and your Phi's means that you can make your mathematics easier without changing your physics. Your electromagnetic field has not changed. The same we will see, we call this a gauge, by the way, a gauge. A change of something in such a way that mathematics become easier, yet your physics stay the same. There's also gauges in general relativity. You can change up your relativity in such a way that your physics is exactly the same, yet your mathematics becomes much, much more easy. In fact, before we go through that calculation, let me already tell you what the reward is going to be, yes? Let me tell you how this is going to make our life much more easy. Let me make some space here. The reward of our playing around with gauges in general relativity is the following. There, okay. We can use gauges to make those two terms go to 0. Not by approximation, not because h mu nu is small or some of those tricks. No, we can change our gauge, our choice of mathematics such that these two terms will be completely gone. Again, we will do this in a moment. But here's the reward. The thing that you end up with then is this one version, 2 time derivatives and 2 space derivatives equals 0. You have either seen this as, I don't know, vibrations and waves, maybe in some other physics courses, maybe in dynamics, we certainly solved it there. Is anyone who knows what the solution is to that equation? This thing equals 0.
Is it the wave equation?
It is called the wave equation, yes. Not coincidentally, by the way, gravitational wave. But do you remember what the functional solution is? Right? We'll prove this in a moment, but suppose that you could. Do you remember what h alpha beta should look like for the remaining equation? See you following along?
That depends on x and t in a certain way. But I
That is
forgot
true.
how it depends on x and t.
Yes. Here, sir.
X plus ct or something.
H alpha beta, this is a mathematical fact that I'm now going to state. H alpha beta, if it just has to obey Lambertian equals 0, then H alpha beta is whatever function. It still has 2 indices, right? Here's still 10 of these numbers. Each of them is a function of space and time because it's something in space and time here. But the equation tells you it has this one particular way that it is only allowed to depend on space and time. And that way is the following: t minus r over c. Well, this is something like this. This is a mathematical fact. This thing, Lambertian equals 0, is solved by whatever function, as long as you make that function depend on space and time in this particular manner. If you don't believe me, take this thing, put it in here, solve it for yourself. You can see that this is true. Now what does that tell us? Physically. Right? We yet have to prove that we can erase this, but suppose that we did. And we now know that whatever this gravitational wave is, I'm really using the name now, not perturbation or gravitational wave, it tells us something. This particular form.
That little extra travels kind of determined by that function, so like a wave.
Well, I mean, the function, what f is, determines what the shape is of
Yes.
the thing, right? And I told you we're going to hit Minkowski space-time, and it will make some perturbation. Now, what the thing will look like, it is dependent on how I hit it. Right? If I just squeeze everything together and then let it go through space, it will have a different shape than when I just jump in there. Or I have two black holes merge against each other or something like that. That will determine the shape. But this equation is very strong. It says whatever the shape is, no matter how you perturb the space-time, it will always have this relationship on space and time.
Gives you the velocity.
It gives you the velocity. It tells you that for every moment in time, every moment in space, the relationship between the two is c. It tells you that gravitational waves, I'm now going to fully use that name, travel with the speed of light. necessarily. We already concluded that in the beginning, right? Because there were masses and such, but we see it happen now. It comes out. It's a mathematical fact. The fact that it depends on space and time in this particular matter tells you they have to go at the speed of light. So we have a very important result now. It doesn't even matter how you perturb space-time. Whether you jumped in or had two black holes collide or squeeze everything together and then let it go, whatever you did, whatever comes out, whatever shape came out, that shape will move through space and time at the speed of light at the moment that you let go. That's what this thing does. It tells you something more too. That's a question that I was asked by 2 or 3 different forms by different people in the break and during the lecture before the break. Who says that this thing exists in the first place? Right? We just assumed that if you take Minkowski plus a little extra, and then we had just assumed that the thing existed. Now, if the thing had not existed, then somewhere in the calculation, mathematically would have said, nope, this thing must be 0. It doesn't. It says, no, it can be anything. As long as it goes with the speed of light. That's a big conclusion. We see now that gravitational waves exist, that they can have any shape, and that they must travel with the speed of light. So, beautiful result, right? Here's your gravitational waves. As long as we can make these vanish. That's the hard part. Ha! Now 4 minutes to do with it.
So you would assume they're the same, but with a different sign, right? For them to vanish, or they're 0, which doesn't
No, what I'm
seem likely.
well, let me just tell you the strategy, and we'll fill in the details over the two tutorials. Yes, I'm just going to make some room there because this is important. Yeah, you must have seen this at some point. If not for this particular application, then at the very least to understand what gauges mean, because you're going to encounter them in many branches of, especially theoretical physics, particle physics, theoretical physics, astrophysics, general relativity, gauges. So we have to go through this. I will tell you what the strategy is going to be. We're going to show that this V, this particular combination, is going to be 0. So not even that these things cancel, not even that they are constant. No, the whole thing itself, the V's are going to be 0. If you choose in the right particular way your gauge. Question is, what do I mean by gauge in this case? I told you generally a gauge means you do something to your mathematics within your physical theory such that the physics does not change. And in electrodynamics, that meant that you change your potential fields by particular ways. Now, what would be a gauge in general relativity? What is it that you can change up a little bit without changing your physics? That's a question to you. Let's see if you can intuitively find the answer to that.
Don't you also have fields in gravitation physics?
Yes.
You have the,
Gravitational fields,
what's
yes.
the phi called? The Newtonian field.
You would call it
Newtonian
gravitational potential, yes.
Yeah, gravitational potential.
Yes, but here you don't have to worry because...
We don't use that?
No, well, we are using that because the magic tensor is a potential field.
Oh,
I
yeah,
briefly
sure.
mentioned this to you in the
Yeah.
break last week, but never really put much emphasis
You
on
can
it.
change the coordinate frames.
Why change the coordinate frames?
It's the only thing I see that makes any sense relativistically speaking, and
Yes.
it doesn't change physics because, well, relativity.
There's a full and complete answer. If there's one thing about general relativity, that was the whole starting point to begin with, was the principle of relativity. You can do this in whatever coordinate frame that you want. So the only thing you have to do, right, whatever conclusion you're going to get, the conclusion must hold in all coordinate frames. So, if you don't like the mathematics, just find another coordinate frame. It's just as valid. That's where the Einstein equations came from to begin with, from the condition that you should be able to, you should be allowed to use this equation in every coordinate frame. Okay, then use the freedom to go to another coordinate frame. Choose a coordinate frame in which this particular combination that I abbreviated by the letter V here, this tensor, is 0.
So is the gauge still adding something to one of the quantities in your
Yes,
equation?
and again I was hoping to do this during the lecture, but I will just put it in the tutorials, make it a fun exercise to do together. We are going to do the following, again tutorial. This is your coordinate frame, yes? is coordinates in which you express your space and time. In our case, it will be t, x, y, and z. We're going to go to another coordinate frame, which I will call a prime frame, as you do in special relativity. Plus, and this is your plus, you're going to add something, plus a little bit extra.
I hate that symbol so much. Can you make it a different symbol?
This is the, unfortunately, this is the gauge symbol that people use in general relativity. I'm happy to change it to something else. In fact, let's call it, the Sidley tensor or something like that.
Much better.
Okay.
Thank you, Ali.
The Xi is the one that people use, okay? So I'm also very bad at these things, but this is the best I can do. Let's call it the Sidley tensor, okay? Now, do you see what we're doing here is that we are, oh, by the way, sorry. This is the original one, this one, plus Sidley tensor. It literally means I have a coordinate frame here, space, time, and I'm going to move to another coordinate frame. That could be a moving coordinate frame, or like a Lorentz transform. That will mean that the Sidley tensor is like a Lorentz transform. It could also be, you know what? Let's make it a completely twisted, rotating coordinate frame. General relativity doesn't care. The whole idea about relativity is it should hold in all. You have complete freedom to choose your Sidley tensor, whatever you want, you will always get the same physics out. Your mathematics will change though. At the moment you go to another coordinate, we've seen this in week 2 when we actually went from Cartesian, say, to polar coordinates. We saw that the metric tensor completely changed. Do you remember that? When we had the Minkowski space-time or Euclidean space, 1, 1, 1. And we went to a spherical coordinate system, the metric tensor completely changed. It went from 1 on 1 to, I forget what it is, r squared, the r squared sine theta or something like that. You still have the same space-time, right? Nothing really has changed, it's just the coordinate in which you wrote it has changed. This is the gauge in general relativity. Just go to a different coordinate frame. Here's the claim. Again, we will go through the full details during the tutorial, but the claim is, if you go to another coordinate system, you can choose your Sidley tensor in such a way that these vanish. We've now really fully made use that we are in general relativity. We have made use of the fact that you can go to any coordinate frame and you would still have the same physics. Now, I don't know what is more beautiful than exploiting this mathematical freedom that you get from having general relativity. So, long story short, we have to go through this in some detail in a moment, but once we have done this, we have seen that this can vanish, and therefore you have your gravitational wave. Alright, I think this is okay for now, yes? So, we have our Einstein equation solved, and we know what gravitational waves do, how they exist. Beautiful. Alright, let's have a break. Do some of these mathematical steps in the tutorial. I might get some caffeine somewhere. Especially for the people who have the evening shift, all the poor people. And include myself, by the way.
I'm sure.